There is a machine buried under the Alps right now, longer than 4 football pitches, heavier than a small warship, and it physically cannot go backwards. Not shouldn't, cannot. The moment the crew starts one of these things forward into a mountain, they have committed to a one-way journey that will take years, and the only exit is to keep cutting until the far side of the Alps opens up in front of the cutting head. This is the strangest engineering bet on the continent, and almost nobody outside the tunnel industry knows it is being made. Start with the object itself, because most people picture something the size of a bus. It is not. A hard rock tunnel boring machine of the kind used under the Alps is closer to a mobile factory. The 4 machines that cut the Gotthard base tunnel in Switzerland measured more than 400 meters from the front of the cutting wheel to the back of the trailing gear. The cutting wheels themselves were 9.43 meters across on the southern drives and 9.58 meters across on the northern ones. Each wheel carried 3,500 kilowatts of power and could deliver a torque figure that means very little in isolation and everything in context. Enough to keep a wall of steel discs pressing into solid alpine gneiss without stalling, hour after hour, for the better part of a decade. Behind that wheel comes the rest of it. Hydraulic thrust rams, gripper shoes the size of garage doors, a control cabin, then a train of trailing gantries stretching hundreds of meters back down the hole, carrying the electrical transformers, the ventilation ducts, the hydraulic power packs, the water lines, the grout pumps, the conveyor belt that hauls the broken rock out, a workshop, a store of spare cutter discs, a toilet, and somewhere in the middle of all of it, a small table where 15 or so people eat their lunch 1,500 meters below a glacier. Now the part that matters. Ask an engineer why the machine cannot reverse, and you will not get one reason. You will get 5, stacked on top of each other, and each one on its own would be enough. The first is geometry. The cutting wheel at the front is the widest thing on the machine deliberately. It carves a hole very slightly larger than the body that follows, because if the body were the same size, it would jam against every irregularity in the rock. That overcut is measured in centimeters. It is generous enough to let the machine slide forward through a hole it has just made, and nowhere near generous enough to let it slide back out through a hole that has since changed shape. Because rock does change shape. That is the second reason. Deep alpine rock is not inert. Under 2,000 meters of mountain, the stone is under pressure that has been building since the African and European plates began colliding. And the instant you cut a void into it, that pressure has somewhere to go. The rock converges. In good granite, the movement is millimeters and stops. In the weak, crushed, clay-rich zones the Swiss call cockyrite, the tunnel walls can squeeze inwards by tens of centimeters, and they keep doing it for weeks. The hole the machine cut yesterday is smaller today. Reversing into it would be like trying to pull your arm back out of a closing fist. The third reason is what fills the space behind. In softer ground, the machines line the tunnel as they go, erecting rings of precast concrete segments immediately behind the shield. The machine on the Italian side of the Lyon to Turin route builds its lining from 8 segments per ring, bolted into place within meters of the cutting face. Once those rings are in, the finished tunnel behind the machine is narrower than the raw bore. The machine has, in the most literal sense, walled itself in behind its own back. In hard rock drives that use grippers rather than a full shield, the walls get steel arches, wire mesh, rock bolts, and 300 millimeters of sprayed concrete, which achieves the same thing by different means. The fourth reason is the trailing train. Those hundreds of meters of gantries are not a tail the machine drags. They are the machine's lungs, its power supply, and its digestive tract. and they sit in a tunnel with only centimeters of clearance, riding on rails connected by ventilation ducting and high-voltage cable and a conveyor belt that is spliced longer every few days. To reverse the machine, you would have to reverse all of it in order without kinking a duct or shearing a cable along a bore that is deforming around you. The fifth reason is the simplest and the one tunnelers actually give you first, usually with a shrug. The discs only cut forwards. A cutter disc is a hardened steel ring that rolls under enormous load and fractures rock by pressing into it, and the whole assembly, the whole gearbox, the whole thrust system is engineered to push one way. Nobody built a reverse into it because nobody could think of a job that reverse would do. You do not buy a machine that costs as much as a stadium and then spend money on a capability the mission does not include. Which brings you to the consequence, and the consequence is the real story. Every single meter one of these machines advances into the Alps is irreversible, not difficult to reverse, not expensive to reverse, irreversible. The mountain closes behind the machine like water behind a ship, and the only geometry in which the crew ever sees daylight again is forwards. Now hold that thought and consider what the Swiss did with it. The Gotthard Base Tunnel runs 57.1 kilometers under the Central Alps with as much as 2,300 meters of rock overhead at its deepest. At that depth, the virgin rock temperature climbs high enough that the working environment had to be cooled with industrial chillers because the mountain itself is warm. Roughly 28 million tons of material came out. The project took about 17 years of construction. 9 men died building it, and the 4 boring machines between them cut more than 85 kilometers of the main tubes. Somewhere in the middle of that alignment, there was a problem that the entire project was, for years, quietly terrified of. It has a name that sounds almost gentle. The Piora Mulde, the Piora Basin. The Piora Zone is a band of carbonate and sulfate rock that geologists knew crossed the tunnel line. At the surface, and for a long way down, that rock is not really rock at all. It is dolomite that has been broken down into fine, non-cohesive grains with the consistency of wet sugar, saturated and under pressure. If the machine cut into a body of pressurized sugar sand 1,500 meters underground, the material would flow into the tunnel, the face would run, and the machine would be buried in a matter of hours. Not damaged, buried, and it could not back out. So, before anyone committed, the Swiss went looking. During the 1990s, they drove a 5.5-kilometer exploratory tunnel purely to get close enough to the Piora Zone to interrogate it. And from that tunnel, they put out 19 directional boreholes, some reaching 350 meters down towards the level where the real tunnel would eventually run. In 1996, one of those probe holes gave them their answer in the most violent way available. Water at a pressure of around 150 bar blew back up the borehole and drove roughly 1,400 cubic meters of sugar-grained dolomite into the exploration tunnel. They could not shut it off conventionally. They sealed the exploratory tunnel with a concrete plug 8 meters thick and walked away from it. That single event could have killed the whole project. If the Piora material extended down to the tunnel horizon, there was no machine on Earth you could safely send through it, and the alignment would have to move at enormous cost, or the scheme would die. The cores told a different story. At the depth where the base tunnel would actually run, hundreds of meters below the disaster, the same geological body was hard, dry, and competent. The sugar was a near-surface phenomenon. The rock at tunnel level was, in the flat language of the reports, suitable for mechanized tunneling. Everything then came down to whether you believed the cores. Because the machine could not back up, There was no version of this where you nosed in, had a look, and withdrew if it turned bad. You either sent a 400-meter machine and its crew into the zone, or you did not. They sent it. The machine was pulled out of the line for a major overhaul first, rebuilt and modified specifically for the crossing, and then it went in on the 29th of September 2008, and it did not stop. Behind the cutting head, the crews set steel ribs at 1-meter intervals and layered on shotcrete to a total of 300 millimeters, and they watched the instruments for the first sign of the walls moving. On the 12th of October 2008, the machine came out the far side of the Piora Mulda. The engineer's summary afterwards is one of the great understatements of modern tunneling. They could not measure any deformation at all. 14 days, years of investigation, one catastrophic borehole, a concrete plug still sitting in an abandoned side tunnel, and the actual crossing took 2 weeks because there was nothing there to fight. That is the emotional signature of no reverse gear. You do not get to test the water. You do the geology until you can stand behind a number, and then you spend the machine. There is one more thing the no reverse rule does to daily life underground, and it is the detail that tunnelers mention when they want to explain the job to an outsider. The cutting discs wear out. On hard alpine rock, a disc might last a few hundred meters before the steel ring is worn flat or cracked, and each cutting head carries dozens of them. Replacing one means stopping the machine and sending people forward, through hatches in the cutting head, into the narrow gap between the wheel and the raw rock face. They work in there with hoists and hand tools, hauling out steel rings that weigh well over 100 kilograms each, with the whole weight of the mountain standing a few centimeters from their shoulders. On a long drive, a crew will do this thousands of times. It is routine, it is scheduled, and it is the only moment when a human being is actually in front of the machine. Every other hour of the project, the safest place to be is behind the cutting head, inside the steel, moving forwards. That is the physical shape of the constraint. The machine's only direction of travel is also the crew's only direction of safety. Not every stretch was so kind. Elsewhere on the Gotthard, the machines hit exactly the crushed, squeezing ground the engineers feared, and the fix was to build deformation into the design on purpose. Rather than fight the mountain with a rigid lining that would simply crack, they used support rings that could telescope and slide, letting the rock converge by a controlled amount before the lining took the load. You allow the mountain to move so that it stops moving. It is a strange kind of engineering humility, and it exists because the alternative, a jammed machine, has no remedy. And in between the crises, there were the days that make tunnelers grin. In 2009, one of the northern machines, nicknamed Gabby 2, cut 56 meters of alpine rock in 24 hours. That was a world record for a machine of that size. 56 meters in one day through a mountain, at a depth where the stone is warm to the touch. The Swiss named their machines the way sailors name ships. The two southern machines were called Sissy and Heidi. The two northern ones were the Gabbies. Crews leave photographs and small shrines on the trailing gear. When you are going to spend 6 years of your life inside a steel tube with a machine that can only go forwards, you tend to develop a relationship with it. Go 150 kilometers east and the same logic is playing out under the Brenner Pass, on the border between Austria and Italy, and it has only just reached its climax. The Brenner Base Tunnel is 2 main rail bores of about 55 kilometers each, with a smaller exploratory and service tunnel running roughly 12 meters beneath them along the whole alignment. Connected to the existing Innsbruck bypass, the continuous underground railway comes out at about 64 kilometers, which makes it the longest such link in the world. The Italian side drove with tunnel boring machines. The Austrian side, working through different ground, used conventional drill and blast. That lower exploratory tunnel deserves a moment because it is the direct institutional answer to the no reverse problem. If your main machines cannot retreat, then you send a smaller machine ahead of them, along the same line, 12 meters down, years early. It maps the geology, drains the water-bearing zones, and gives the main drives a rehearsal of everything they are about to meet. It is a scout that takes the risk so that the expensive machines do not have to. On the Lyon to Turin project, the same trick was used with a machine called Federica, which cut the exploratory bore in 2019 through precisely the ground the main machines would later face. At Brenner, the exploratory tunnel met its counterpart from the other side in September of 2025, and the two headings, driven towards each other from different countries through 1,400 meters of mountain, missed by a few centimeters. Then, on the 28th of July 2026, the main tubes broke through. The machines named Virginia and Flavia, working up from the Italian side, met the Austrian excavation roughly 1,400 meters below the Brenner Pass, and the survey deviation in the main tubes was smaller still than the exploratory tunnel's few centimeters. Sit with that number for a second, because it is where the no reverse gear rule turns from a constraint into a discipline. Two teams start on opposite sides of a mountain range. They cannot see each other. They cannot use satellite positioning underground. They are navigating by gyroscopic instruments and laser sightlines down a bore that curves, and every measurement error compounds over tens of kilometers. Neither machine can back up and try a different line, and they meet after years within a few centimeters. That precision is not a flourish. It is a requirement created directly by the machine's inability to retreat. If you could reverse, a bad alignment would be an expensive nuisance. Because you cannot, a bad alignment is a machine entombed in the wrong place under an international border. So the surveying gets obsessive, the exploratory tunnels get dug, and the boreholes get drilled by the hundred, all to buy certainty in advance of a decision that cannot be revisited. West of both of these, under the mountains between France and Italy, the Mont Cenis base tunnel for the Lyon to Turin line is still being cut, and it is where the difficulty is most visible right now. A machine called Viviana is working a 9-kilometer stretch of the northern tube between Saint-Martin-la-Porte and La Praz in France. It is 10.4 meters in diameter, carries 61 disc cutters on its head, has 8,100 kilowatts installed, rides on 10 trailing gantries with the conveyor built through them, and works with a crew of around 15 aboard. On a good month, it is expected to make between 300 and 450 meters. Between Saint-Martin-la-Porte and La Praz, it slowed right down, and the project said so publicly, because the ground there had been flagged years earlier as one of the most sensitive points on the whole alignment. Nothing broke, nothing was buried. The machine simply entered ground that everybody knew would be bad and moved through it at the pace bad ground allows, guided by what Federica had learned in the exploratory bore. That is what a mature answer to no reverse gear looks like. Not heroism, not improvisation. A scout tunnel, a forecast, a schedule that already contains the slow section, and a crew that does not panic when the advance rate falls because falling was in the plan. The alternative is worth describing because it happens. When one of these machines does get stuck, the options are short and all of them are ugly. You can drive a rescue shaft down from the surface, which is straightforward under a city street and effectively impossible under 2 kilometers of Alps. You can hand mine forward from inside the machine, sending people out through the cutting head into unsupported ground to grout and stabilize the face by hand, which is the most dangerous work in the industry. In one case, in Toronto, Freeing a trapped machine took 19 months and millions of dollars. In China, engineers recovered a buried machine by sending its twin from the parallel tube to reach it. And frequently, when a machine reaches the end of a drive somewhere it cannot be extracted from, the answer is the one that startles people who hear it for the first time. The crew strips out the valuable parts, and the rest of the machine is left in the ground. A concrete chamber is cast around the shell, and it becomes part of the geology. The cost of retrieval is greater than the cost of the machine. That is the ordinary fate of these things, even when everything goes right. A machine is designed for one specific mountain, with a cutting head sized for one specific bore and cutters chosen for one specific rock. It is built. It is assembled underground in a chamber cut for the purpose. It drives for years. And at the far end, it either comes out into a reception pit and is taken apart for scrap and salvage, or it is buried where it stopped. There is no fleet. There is no depot where the machines go between jobs. Sissy, Heidi, and the two Gabbies were built to eat the Gotthard, and they were, in every meaningful sense, consumed by it. And this is where the metaphor stops being a metaphor. The tunnels these machines cut are themselves projects with no reverse gear. The Gotthard was approved by Swiss voters and then built across 17 years through changes of government, changes of economic climate, and a full generational turnover of the engineers who designed it. The Brenner has been under construction for well over a decade and will carry trains in the 2030s. The Lyon to Turin link has been fought over politically for 30 years and is still being cut. Each of them was authorized by people who would not see them open. On the strength of traffic forecasts for a Europe that did not yet exist, to move freight off alpine roads and onto rails running flat and deep, beneath passes that have shaped the continent's trade since the Romans. Once you start, the money is in the ground. You cannot recover a half-finished base tunnel. You cannot repurpose 40 kilometers of bore under a mountain range. A political decision to abandon one of these projects halfway does not return anything. It simply converts billions into a whole. So the projects, like the machines inside them, acquire a momentum that has nothing to do with enthusiasm and everything to do with geometry. The only way out is through. There is a particular hour on every one of these drives that no photograph captures. The machine has been running for years. The crew has changed several times over. The rock ahead is unknown in detail, mapped only by probe holes and seismic guesses. Behind them, the tunnel narrows into finished lining and disappears into a string of lights that runs 20, 30, 40 kilometers back to a portal somebody's father worked at. And the shift starts, and the cutting head turns, and the thrust rams push, and the machine moves forward by another few centimeters because forward is the only direction it has. They will keep doing that until the mountain runs out.